So far, we have learned several basic tools of Fourier analysis, and we know the Fourier representation for continuous time periodic signals, continuous time aperiodic signals, and discrete time periodic signals. And now, to complete the set of Fourier analysis tools, in these modules, we will learn the Fourier representations for discrete time aperiodic signals, and that will lead us to discrete time Fourier transform development. And in this development, we will follow the similar strategy that you have already seen for the case of continuous time Fourier transform development. That is, we will start from an aperiodic signal, and then we will periodize this signal by repeating the non-zero parts of this signal at regular intervals separated by long intervals where the function is zero. And then we increase the time period and the frequencies get closer together. Fourier series coefficients seem to track some envelope function. But then we introduce the transform function, which in fact is the envelope function that the Fourier series coefficient are tracking. And finally, we take the limit and make the time period go to infinity. In that limit, we analyze the behavior of the Fourier series synthesis equation, and we complete our result. So in this development, we will use the discrete time Fourier series equations for discrete time periodic signals. So here, if x tilde n is a discrete time periodic signal, we have its Fourier series representation as a linear combination of discrete time complex exponentials. Here, the summation k is over a range of capital N successive integer values starting from any value of k. And the Fourier series coefficients we can find with the help of analysis equation. Once again, this summation is over a range of capital N successive integer values starting from any value of n. The interesting thing about discrete time Fourier series coefficients is the periodicity of these coefficients. These coefficients have the same time period, capital N, as the sequence itself. And in these representations, we use the discrete time complex exponentials, which have different properties compared to their continuous time counterparts. First of all, if we have a discrete time complex exponential at frequency omega naught plus 2 pi, then it is the same as the discrete time complex exponential at frequency omega naught. So we have this frequency wraparound effect, and therefore frequencies are only unique in an interval of length 2 pi. We can take any interval, but in general we take the interval going from 0 to 2 pi or from minus pi to plus pi. Then the rate of oscillation is maximum when omega naught is equal to 2 pi, or if omega naught is any odd multiple of pi. The discrete time complex exponentials that we use in the discrete time Fourier series expressions, these are periodic with period capital N, because we are considering the integer values of k and n. Now, let us develop the discrete time Fourier transform. Here we consider a general aperiodic sequence which is non-zero from integer values of minus capital N1 to capital N2, and it is 0 for all the other values of n. So we construct a periodic signal x tilde n for which xn is one period. So x tilde n is periodic and its time period is represented by capital N, and the fundamental frequency is omega naught equal to 2 pi divided by capital N. And then in the limit when capital N approaches infinity, x tilde n is equal to xn for all the values of n. So we will see the behavior of discrete time Fourier series synthesis equation in this limit. For x tilde n, we can write the discrete time Fourier series equations. So here I have written down these equations, and from these equations, we will see the further development. So I start from the discrete time Fourier series analysis equation here. We can take this summation over any consecutive n integers. So I take this interval from minus n1 to n2. From this analysis equation, we write ak equal 1 over capital N summation n equal minus n1 to n2 x tilde n e minus jk omega naught n. And here I have replaced 2 pi over capital N with omega naught. Now we notice that in this interval x tilde n is the same as xn. So this is equal to 1 over n summation n equal minus n1 to n2 xn e minus jk omega naught n. And now since xn is 0 outside this interval, so the limits of this summation can go from minus infinity to infinity. So here let us write n going from minus infinity to infinity xn times e minus jk omega naught n. So I bracket this term and introduce a transform function. Transform function. And our transform function now is capital X e j omega equal summation n equal minus infinity to infinity xn e minus j omega n. If we substitute omega equal to k omega naught in this transform function, we will get this Fourier series coefficient. So once again, with the introduction of this transform function, Fourier series coefficients are the samples of this transform function at omega equal to k omega naught. And because of the properties of these discrete time complex exponentials, we can very easily show that the transform function capital X e j omega is in fact a periodic function with period 2 pi. So let us show the periodicity of this transform function before doing further steps on discrete and Fourier transform development. Here, for example, if we replace omega with omega plus 2 pi, then on the right hand side we will get n equal minus infinity to infinity xn e minus j omega plus 2 pi n and n equal minus infinity to infinity xn e minus j omega n e minus j 2 pi n, and e minus j 2 pi n is 1. So this is equal to capital X e j omega. So let me write it down here. The transform function is periodic in variable omega with period 2 pi. Okay, so let us continue the development of discrete time Fourier transform. AK is 1 over capital N, and the kth coefficient is the sample of this function taken at omega equal to k omega naught. And we plug AK into equation 1. So we get x tilde n equal summation k equal n 1 over n x e j k omega naught e j k omega naught n. Let us replace 1 over n with omega naught divided by 2 pi. So x tilde n now is summation 1k, and let me bring 1 over 2 pi outside. Inside we have capital X e j k omega naught into e j k omega naught n. And now we take the limit. In the limit, and this capital N approaches infinity, x tilde n approaches xn. Here omega naught approaches 0, and by the same arguments as we saw in the continuous time Fourier transform development, this summation will turn into an integral. But because this summation is over capital N successive integer values, so we will see that when n approaches infinity and omega naught is approaching 0, the total interval of integration will always be 2 pi. And we get limit x tilde n equal to xn, and the right hand side it is 1 divided by 2 pi. We have an integral over an interval 2 pi, and k omega naught, it becomes a continuous variable e j omega n times d omega. So here we have the synthesis equation, and this together with the transform equation e j omega equal summation n equal minus infinity to infinity xn times e minus j omega n completes our development of discrete time Fourier transform. So this equation, this is discrete time Fourier transform synthesis equation, and this one is discrete time Fourier transform analysis equation. So have the discrete time Fourier transform for aperiodic discrete time signals. And there are some similarities and differences with the continuous time Fourier transform case that we will highlight now. So similarities with continuous time Fourier transform CT-FT. First of all, aperiodic sequence can be thought of as a linear combination of complex exponentials number 2 capital X ej omega is referred to as the spectrum of Xn because it provides information on how Xn is composed of complex exponentials at different frequencies. And discrete time Fourier series coefficients of discrete time periodic sequence x tilde n can be thought of as scaled and equally spaced samples of the discrete time Fourier transform of its corresponding aperiodic sequence. So here, recall the square wave example in the continuous time case, where we saw how the Fourier series coefficients are tracking the envelope, and same here, discrete time Fourier series coefficients, we can get them by sampling the discrete time Fourier transform analysis equation. And now let me highlight the differences. So differences, these are more crucial and important. The first thing to notice that we have proved above, Ej omega is periodic. So it is enough to specify x e j omega over an interval of length 2 pi, because its period is 2 pi. Number 2, in the dt ft synthesis equation, limits of integration are also over an interval of length 2 pi. And the third difference, xn is a discrete time function, while x capital X e j omega is a continuous function in variable omega. So In the continuous time Fourier transform case, both the synthesis and the analysis equations, Fourier transform and the inverse Fourier transforms were integral equations, and they were giving us continuous functions in time and in the frequency. But here, xn is a discrete time function, but its transform capital X ej omega is a periodic continuous time, continuous function in variable omega. And because of this, there is a duality between discrete time Fourier transform and continuous time Fourier series. Fourier series. So if you recall, in continuous time Fourier series, we have a periodic continuous function in time domain. And the analysis equation of continuous time Fourier series gives us a series representation. The analysis equation provides us the Fourier series coefficients, which are discrete sequence. So here we have capital X ej omega. It can be represented as a linear combination of complex exponentials, and the discrete time Fourier transform synthesis equation here, it looks very similar to the continuous time Fourier transform analysis equation. And if we switch the roles of omega and n and do a reversal of sign, we have this duality between discrete time Fourier transform and continuous time Fourier series.